Hello everyone, and welcome back to my series of videos where I'm solving LeetCode problems. And the problem now is counting bits 338. So what's it about? Given an integer n, return an array n's of length n plus 1 such that for each index, and indexes from 0 all the way to n inclusive, the answer of 1 is the number of 1s in the binary representation of 1. So if input is 2, then we have an array of length 3. So 1, 2, 3. And the output is 0, 1, 1 because it's the number of 1s in the binary. So the number 0, 1, 2. 0, 1s, 1, 1, 1, 1. And same thing here. Let me zoom in a little, maybe you can see better. Same thing. 3 has 2 1s, 4 has 1 1, 5. Okay, so solution, def count bits, return a list of integers. Let's make a directory. 338 counting bits. Code 338. Let me just turn up my music a little. And let me turn it down. Okay. So let me copy this. Solution dot count bits and pass solution dot count bits of 5. What's 5 that we have? Yeah, 5. So first of all, we need to iterate for I in range n plus 1. That will return us, let's just check, it will return us the numbers from 0 all the way to 5, in this case inclusively. So let's just run the code. Yeah, all good. 1, 2, 3, 4, 5. And now, what do we do? And now I'm going to create another function which is count bit. Count bits of number. I'm just going to separate things. And equals int. And it returns an integer, the number of bits. So total ones is an integer that starts with 0, and we want to return total ones, and total ones plus equals the number of bits on that number. Count bits of number I. So let's count the bits of a number. One way of counting the bits of a number is doing a bit shift operation. So let me just check something on the pro. N is smaller than that. So let me think. Okay, let's count the bits. So one way of doing it is to we can do for I in range 32, and we can do bit equals n shifted by I and 1. And what does this mean? Let's say count bits, it's integer and it's 0, and I just increment this. Return count bits. Let's see how this works. So n is 0, count bits is 0. Let's just check for 1. N is 1, count bits 1. And this 2, count bits 1. Okay, so what's happening? I did a video on another problem where I teach everything about bit shifting operations, and it's all the way back. I don't remember the name. Add binary, I think. No, not add binary. Reverse bits, number of 1 bits. So I have videos on that, so please go and check it. So coming back here, but basically I'm just checking if the last bit is 1, and I'm shifting all the bits to check if the last bit is 1. And let's return that. Total ones of 5 is 2. Oh. Plus equals. So total ones is 7. And oh yeah, I don't want to output this. I want to output a list. Return value is a list of integers that starts with an empty list. So return value dot append to the end of the list. This. So let's go. Let's check. 0 1 1 2 1 2. 0 1 1 2 1 2. Okay. Let's submit this. Let's see if we're lucky. Okay, so it works, but it's slow, and I think I can help you. I think I can do a better solution, and how can I do that? So at this moment, let's say we have 100 numbers. We're counting the bits on all of them. However, I think we only need to count the bits of the numbers that come after a potency of 2. And we can check the ones before. I think I can do that. No, that doesn't make so much sense. Or does it? I don't know. Let's check what other people did. ON solution plus intuition. Okay. So basically what this is doing, it's counting the checking. Okay. The vector, so list of integers answer has this length, and for I equals 1, yeah, because the first one is 0, I think it just initializes with zeros. And for 1 all the way to n, and we increment it. Let's do that. So it's 0 times where's the times in this keyboard? I keep changing keyboard. Oh, it's 8. I keep changing keyboards and that's a bit bad. So n plus 1. And so for this range, and now what was it? If answer of I continue. Yeah. Okay. So only the numbers, only the index 0 will be 0. Everything else will be something different. So if return value of I means if we already have a value, we continue. Yeah. So that's good. Continue. And if not, answer of I equals answer of I minus 1 plus 1. It's not necessarily true. Unless we only get here if this doesn't happen and this will happen to make this happen. Okay, so in some cases, so I can say that return value of I equals return value of I minus 1 plus 1. And now I can say that while I'm doing powers of 2, while I'm multiplying it by 2, I can say that the number of bits is the same as the number of bits before. So what is the logic here? So let's say we have number 1. Okay, 1 is equal, we're iterating from 1. 1 is equal to the number of bits of 0 plus 1. Okay, good. Then we get to number 2. No, we don't get to number 2. We're still in number 1, and we do, that's this cycle over here. So we say, okay, 1 times 2 is 2. We know that 2 has the same number of bits as 1. Let me just, number of bits is 0, number of bits is 1. 2 has the same number of bits as 1. And 2 times 2 is 4. 4 has the same number of bits as 2. So, and 1 as well. So 1. And we go to 8. Oh wait, 8 is bigger than 5. Okay, so we stop. So we were at number 1. Then we go to number 2. And it exists 2. Okay, then we go to number 3. 3 is equal to the number of bits of 2 plus 1. This is true. And we do the same thing. We check for 6. Oh, but 6 is bigger than 5, so we don't do that. Then we go at 4. 4 already exists. Then we go to 5, and 5 is the number of bits of 4 plus 1. Okay, so this logic works. Pretty interesting. Pretty cool. So now we do for j in range 1 all the way to n. No, at this, I think Yeah, I think we can do that. No, let's do a while loop because it doesn't really matter. J equals 0 or 1 while j times 2 what was it doing? J equals I times 2, yeah, I times 2 while j is smaller than n. I think you can say smaller or equal to n. So we can say that return value of j is equal to return value of I. And then we repeat this. See if this works. Sorry, not I, j. We're multiplying j by 2. So return value is 0, 1, 1, 2, 1, 2. Okay, let's submit this. Okay, we have better results now. Like way better results. So I hope you guys enjoyed it. See you later.